All right, so we're going to go into hyperbolic geometry or hyperbolic trig functions tonight, which is something that you very rarely see. However, there is use cases for it. And I'll show you a couple of those, but I'm going to show you more of the notation and what it means, and we'll do the derivatives and stuff on it. So it won't be too bad today. However, I did find the answer to our question. So what I found is that arcsine actually came from, because when you're looking at sine, cosine, and tangent, you're typically looking for sides or the actual answer. When you're going the opposite direction, you're looking for the angle. When you're looking at the angle in the unit circle, it is an arc. So that's where arcsine came from, and that's why they use that terminology. However, in 1847, and I honestly can't remember the guy's name, some mathematician who actually won like a whole bunch of awards, started using inverse trig functions. And he wrote it as the sine -1 because he was looking at the inverse of a function symbol. So when you're looking for the inverse of a function, it's f -1. So he took it as, okay, that's the inverse of a function. Sine is a function, so we're going to use the same symbology there. What I did find, though, is that since like 2008, all the standards, like the actual standards and everything else, all go back to the arc symbol because of the confusion that we were finding in class where with the square and stuff like that. So the actual arc is becoming a lot more popular in use cases in engineering and physics and everything else like that because of the confusion bias. But that's why, because it has everything to do with the inverse function.
The reason they did this, they were using that instead of arcsine. They used arcsine for the other.
No, they used arcsine, arcsine, and arctangent were being used, but back in the early 1800s when he came up with this one, it wasn't widely used at that point. Like they were still trying to figure out like what terms and stuff like that they were using. So he formalized using the -1s for the inverse function rules, and he put that forth. That's why that came out. The arcs and stuff like that had been used previous, but nobody ever actually formalized that use case. So going forward, you had almost like the metric and the standard system. You had two different systems being used to the same thing, or Newton and Leibniz. Same concept, two different ways to write it. And he was English, and the English had a tendency to continue using this notation, where other parts of the world were all using the arc notation. So, yes. Yep.
Very confusing.
So, but I'm like, oh, and it's just like everything else. Like when you look at it, it's like, okay, now that makes sense. It's like, why to do so? Okay, at least it wasn't just some random, hey, let me do this. He actually had a reason why he did it that way. It just made it more confusing with other ways that we actually write it. So, that's why. All right, so here is hyperbolic functions. So, actually, I'm going to make this a little bigger since we don't really need the name of it. So when you're looking at the trig rules, sine, cosine, and tangent, they're all dealing with a unit circle. That's where the basis of them are. So when we're looking at the hyperbolic trig functions, sine h, cosine h, tangent h, they aren't based on a unit circle. They're based off of a hyperbola, which is really confusing and crazy. There's actually an entire field of math called hyperbolic geometry, where you actually are not using the rule in geometry where a triangle has 180 degrees, that rule. So hyperbolic geometry actually eliminated that rule completely because the people who were doing it and actually created this claim that Euclid never actually formally proved that theorem, that a triangle has 180 degrees. So, or that the parallel lines cross and the angles are the same, which makes sense, but he never proved it. So in hyperbolic geometry, it's actually not using a flat plane, it's using a curved, and those rules actually don't exist. So in hyperbolic geometry, a triangle can actually have 0 degrees of angle. Because as the sides of the triangle go out to infinity to the edges, they actually never meet. Just like a hyperbola goes to the asymptotes but never actually touches the asymptotes. That's how they design the triangles. crazy pieces of math. The reason why we look at it actually, though, is less to do with the hyperbolas and stuff, but more because the E has a tendency to come up quite a bit when we're looking at different modeling situations. So the hyperbolic sine, or sine h, is e to the x minus e to the negative x over 2. So it's just an easy way to model that formula. So if you look at it, the only two you actually have to really remember are sine and cosine, because all the rest are just the actual trig rules. Cosecant goes with sine, secant goes with cosine, tangent is sine over cosine. All those rules still apply. It's just the sine and cosine that are different. And the only difference between the two is the plus or minus. Sine is negative and cosine is positive. So I would only really, if you want to save space and write things down, you really only need those two, because the trig rules work on the rest of them. All right. Here's two examples of where this stuff is actually used. This is known as a catenary. It's a wire hanging between two towers. And this is actually, stop moving. That's actually the equation that models that shape. It kind of looks like a parabola, but it's not. So that's the equation that actually would model that curve. And it's also used in waveforms and fluid movement and stuff like that too. So you will not need to know this. At least not for here. No, I do not know the equation anything with fluid dynamics. That was the picture from the book. It was like, here is a couple places it's used. Okay. All right. You'll notice that actually pretty much all the rules that work for the trig work for these. That's actually one of the reasons that they used the trig rules. What they found was that model of that E equation, when they did all the actual steps and everything else, it still modeled all the same stuff that had to do with the trig function. So the sine of negative x is the same as negative sine of x. The cosine squared, in this case, it's cosine squared minus sine squared instead of cosine squared plus sine squared is equal to 1. The 1 minus tangent squared is secant. So it's like those rules still apply. Adding rules, the sum addition rule or the angle addition rules still apply. So the rules are still very similar in action. All right, let's do a couple. All right, so one of the rules that I just showed you was the cosine h squared minus sine h squared is equal to 1. So let's actually show that. So the easiest way to do this is to go back to what the actual rules were. So what was cosine of h? It was e to the x plus, no, the cosine was plus negative x over 2 squared, and then minus e to the x minus e to the negative x over 2 squared equals 1. So my goal is to prove that's true. All right, so let's see if we can simplify this all down. So we've got e to the x squared. No, actually, not e to the x squared. It's e to the 2x. Because e to the x times e to the x, which is e to the 2x. And then we got plus e to the x times e to the negative x is e to the 0, which is 1. So this is e to the x times e to the x. This is e to the x times e to the negative x, and it's 2 of those. And then it's e to the negative x times e to the negative x. So I've got plus e to the negative 2x. And that's all over 4. And then I've got minus. The only difference between this one and the one we just did would be the middle term. So I got e to the 2x minus 2 plus e to the negative 2x all over 4. Any questions on how I got any of those numbers up on the top? Or does my red scribbling make sense? So what's x to the third times x to the third? Ignore the problem on the board. X to the third times x to the third. When we're multiplying like bases, what do we do with the exponents?
Yeah.
We add them. Okay, so e to the x times e to the x, same base, add the exponents. X plus x is 2x, not x squared. Because like 3 plus 3 would be 6, so it's x to the 6, which is x to the third times x to the third, not x to the 9th. So that's where the e to the 2x comes from. It's also where the e to the negative 2x comes from. Because negative x plus negative x is negative 2x. The middle one, x plus negative x, is 0. Anything raised to the 0 power is 1. So that's just 2 times 1. Because when you're foiling, we have 2 middle terms. Since it's a perfect trinomial, it's the same thing. So what we end up having here, that e to the 2x and that e to the 2x cancels each other out because they're subtracting. That e to the negative 2x and that e to the negative 2x cancels each other out because they're subtracting. So I'm left with four over 4, which is 1. Because 2 minus a negative 2 is 4.
Two minus negative 2.
2 minus negative 2 is, and my denominator is 4. And 4 over 4 equals the 1, which is what we're trying to prove. It would be negative 2 e to the 0. Because it's the same rule that applied to the first 2 that I got. Because you have e to the x times negative e to the negative x. Okay? We're not going to do b. Because you're not going to do it this way. You're actually going to. I'll show you. It's fine. It's actually a good idea to understand proving things, especially considering I said that Euclid missed something, and this is why all this exists. So whenever you're proving things, you have to start off with stuff you already know. And you can't use things that you haven't already proven. So for this example, we started off with the definition. We had the definition of sine h, and we had the definition of cosine h, and we proved the first one. So we have a definition that was given to us, and we use that to prove the first one. Since we've proven the first one, we can now use the first one. So let's take the first one. If I take, so I know that this right here is sine over cosine. Okay? So if I can get that to be sine over cosine, I'm good. So let's divide everything by cosine. As long as I divide everything by the same thing, did I change the problem? No. Cosine squared h over cosine squared h is 1. Sine over cosine is tangent. 1 over cosine is secant. And I proved that one. Did anybody actually take a geometry class in high school that was a proof-based geometry class?
I don't know, but it was a lot less than the previous years.
Yeah, they don't really do it much anymore. So a proof-based geometry class is basically what I was just saying there. You can't use something until you've proven it. So a true proof-based geometry class will start off with constructions and simple definitions and the postulates. From that, because you need some basic framework to be able to start from. So you have some basic things that are either common sense or can be defined. And then from that, you build up the rest of it. So in Euclid's rules, one of his postulates was that if you have two parallel lines and you cross a transversal, the opposite interior angles are equal.
Oh yeah, we had to write down.
Yeah. So from those basic 5 postulates he came up with, you then start proving out all the other rules that you know. Once you prove it, you can use it. So when you prove that a triangle has 180 degrees in it, you can use that to do problems. So it's that type of a class.
We use this kind of, we just use that, I guess, shapes.
Yeah, oh, absolutely, yeah. When you get, depending on, because very few high school-based classes would get into the proofs of the trigonometric identities and those type of things. However, depending on how you got taught pre-calculus here, one of the things you're supposed to do is actually look at proofs of the trig identities and using the trig rules to actually prove concepts. So, yes?
How did you get, how were you able, why did you use cosine h squared x minus sine h squared x?
Because I already proved that. That was the first statement. That was what I proved in part A.
Okay,
So since I've proven it, and notice when you're proving things in math, you're using stuff you already know that is absolute fact. So we had the definitions of sine and cosine. That's what we did here. So we had those are the definitions. From that, we just used basic algebra and rules that we know work to simplify the problem down and prove that that was 1. Since we didn't use a value, since I didn't plug something in for x to see if it works, I used the actual algebra and the definitions to prove it. That means that is always true no matter what value of x is then. So since I've proven it algebraically, I can then use it. Since I had it, I might as well use it to do the next one.
But why did that part turn into 1 minus 10 h
Because I know, so tangent in general is what? Sine over cosine, correct?
Okay, now I see.
So I knew my middle one had sine where the tangent was.
Consider identity.
So it's like, okay, if I take sine and cosine and divide them, I'm going to get tangent. Because that's an identity that I know. That's the definition of tangent. So since I knew that would work, and sometimes when you're doing proofs, you literally try things. All right? Not everything you're going to try is going to work, but you try something that you think might work and see if it works. Like in this one, I knew that that was going to give me tangent, and then I divided them all to see if it comes out to the rest of it works. If it didn't, I'd have had to try something else. So that's what annoys more people about the proofs. That's what's going to cause us the most trouble trying to write this book, is because everybody's got different ways on how to prove things. And trying to get the teacher to be able to say, yes, this is right, without actually having them understand everything behind the scenes is going to be difficult to do. Which is why we're pushing that book off till next year instead of doing calculus first. So, and also why most teachers don't teach it anymore in high school, because it is not an easy class to teach. So it's one of those ones that you really have to understand things, and you have to be okay with people doing things not the way that you like them to do it. So, which most teachers have a problem with. All right. Let's go to calculus. It's basically the same thing. Look at the rules. What was the derivative of sine? What's the derivative of cosine? So that's really that's one difference. It's not negative, it's just sine. The derivative of tangent is secant squared, so that's the same. The derivative of secant is secant tangent, so that's the same. I believe the other two actually are the same too. Might be a sine.
That one's supposed to be positive.
Yeah, I think that's what I said. I think the signs are different.
That one's sign different and that one's sign different.
Yeah. So it's just little things, but they're basically very similar to what it is.
Okay, that's what you're saying.
Yeah.
Either way, it's not hyperbolic, it's positive.
Right. It's positive instead of negative.
That's different.
So I will tell you the only one you're going to need to know for the test is secant. Or I mean, not secant, it's sine. That's the only one you're going to need to know.
Sine goes to cosine.
Is the sine equals cosine. Well, we're going to use more of them in a minute for these problems. The only one you're going to need to know on the test is sine.
Yeah, I have this little rule in my head. If it started with a C, you get a negative when you turn into a derivative, and now you mess it all up.
That's just the complex ones that are like crazy backwards ones are negative.
Yeah. And sine and cosine basically just keep flipping back and forth instead of changing their signs. All right, so we're good with those? All right, let's do a couple. And it's like, in all honesty, when I've taught Calc 2, I almost always skip the problems that have the hyperbolics in them just because most people don't ever see them. However, I inevitably, because of the way that I assign homework, I don't say, here, do these problems. So inevitably, every single time I've done this, I've always got to ask the question, how do you do this one? And it's always a hyperbolic one. So I figured I have the time, and I needed to cut something out, so I figured, you know what? I'm going to introduce this so at least you guys have seen it before. So if you ever actually see that H somewhere else, you know it's not just something crazy. There actually is a meaning behind it. It's not just like a constant or something that they threw in there and didn't really mean much. So it's always good to see that notation and understand like at least what it is, instead of maybe not being able to figure it out exactly, but at least knowing that it is actually a term. So, all right. So y equals the cosine h, or the hyperbolic cosine of the square root of x. So how am I going to do the derivative of this one?
Same rule.
Yep. And it's also a great way to practice the other rules that we're still using. So u is going to be what?
1 x,
Nope.
square root of x.
Yes. So remember that is x to the 1/2. So u prime,
Square root of x.
right, 1/2 square root of x. We've seen that one so many times, you've probably just pretty much memorized that one by now. All right, so we've got y is cosine h of u. So y prime is sine h of u, u prime. So I've got sine h of the square root of x divided by 2 square root of x. Resist the urge to cancel the square root of x's, even though they're there. I know. I know.
Did you do that with the product rule, or, I mean, I know it probably takes way longer, but is it possible to do it with the product rule?
No, because it's not a product. That's why I said resist the urge to the square root of the same concept. That's not multiplied by that. That is actually part of that. Yeah. So, one of the things we actually did in our book, anything inside the function like that has parentheses around it, because it's just like sine of x squared. It's that x squared is part of the sine. It's not sine times x squared. And I think that's part of the thing. Like when you start seeing like cosine h, those other terms, it's like, okay, is this really just like cosine, or is it cosine h? Like it's that concept there, and that's why I kind of wanted to introduce it to you guys. So, yeah. Well, there's no space, so it's one word. Yeah. So. All right. Huh? Hypercosine. That works too. I wonder if actually. They actually say hyperbolic cosine. So.
Yeah. Sure.
I like hypercosine. I like that better. I agree. These are the derivatives of the inverse ones. Same concept. And actually, they're again very similar to what the derivatives of the other ones are. Some signs are different, things like that there, but very similar in their makeup.
These are all booked, right?
Yes. Yeah, I literally copied and pasted this from the book. Cough. It's like they almost make words, but not quite. It's like costs, It's like cash, but no, it's an A-O instead of an A. Cough is just missing the L. They're almost words. And we wonder why math people don't spell very well.
They have to spell well, or else you're not having fun.
It's like, I'm a horrible speller. I really am. Spell check was the greatest thing in the world that ever happened to me. And even when I program, I'm a horrible speller, but it's all syntax, which I can do those things fine. It's because when I was in school, I was taught phonetically how to, like, I was the generation of phonics. So I can pronounce things, I can read things, I can do those things because it's all phonetics. So when I spell, I want to spell phonetically, not how it's actually spelled. So I say things and I spell them the way they sound, which, as we know, English doesn't work that way. Yeah, that was my generation.
They don't seem the exact same.
Huh?
Tangent, arc, hyperbolic, tangent.
Well, they are actually. They actually are the same. So the only difference, so actually, they even have like an actual, underneath this box it says, notice that the formulas for the derivatives of tangent, the hyperbolic tangent and hyperbolic cotangent appear to be identical, but the domains of these functions have no numbers in common. Hypertangent is defined, because I like that much better than hyperbolic, is defined for when the absolute value of x is less than 1, so it's between -1 and 1. And hypercotangent is when x is greater than 1 or less than -1. So it's the opposite direction, because cotangent does the little loops above, and then tangent is the s. So it's like it's the opposite ends of the things. Technically, both of those would give you all real numbers, which kind of makes sense, because cotangent times tangent would actually cancel each other out. So, all right. Hyperarc cotangent, yes. We're not going to do the proof one. We'll do this one. Just because I think this one's fun. All right, I'm going to rewrite this one a little bit just because of the way it's written. And I want y prime. I didn't want the extra parentheses to mix you up. All right, so what's u? Yes. So, okay. So now I have y equals the arc hypertangent of u. All right, so what's the derivative of that? Squared. And then times u prime, right? Okay. So All right. So let's plug in what we know. So I have 1 over 1 minus what's u? So it's sine squared x. And u prime was cosine x. All right. So what's 1 minus sine x or sine squared x? So this is where we would have to use some of those trig identities. We know this is true. So cosine squared x equals 1 minus sine squared x, right? This is where those rules come into play. It's not that you have to use them necessarily to do the problem. It's you end up having to use them to simplify the problems. That is, yes, that's a Pythagorean identity.
I don't.
So most of you weren't here when I said this last week on the actual review test. I think I told you at the end. I will not put something on the test that I did not put on the review test. So if you need to use an identity in the review test, you'll have to use that identity in the actual test. So like if this identity is on the actual review test, you're going to need it on the actual test. If it is not on the actual review test, you will not need it on the actual test to do the problem. Okay? So you can base your study off that sheet. So that's why I put the rules at the beginning. Like those are the derivative, like the identity derivatives that you're going to need to know instead of this massive list of ones that you might need to know. These are the ones that you're absolutely going to need. So, all right, so 1 minus sine squared is cosine squared x. So that's cosine squared x. So that would be 1 over cosine x, which is, so y prime is secant x. So, and that's actually the hardest part probably of the trig is that it typically does reduce down to something very simple. You're really not normally going to have something crazy looking with the trig problems. And notice that it's not hypersecant, it's just secant.
So 1 over cosine of x equals secant of x?
Yes, because that's the reciprocal of it. As I said at the beginning, the hardest part of trig is, the hardest part of calculus is not the calculus. Like, for all intents and purposes, even to this is easy. Like that, one quick chain rule, one quick derivative, you're done basically. To get from here to here, that's all the algebra and the pre-calc stuff, which is what normally people fall apart on. I will tell you, like, if this was on the test and grading it, you get most of the points. Because again, I'm testing you on that. I'm testing to make sure you understood the chain rule. I'm testing to make sure you understood that the rules. Like I wanted to make sure that you understood the derivative of hypertangent, those type of things. Like those little, hyperarctangent in this case. Those little things. So that's why showing all your steps and showing all your work is very important, because that'll help me understand, okay, yes, they understood what I was talking about. They just screwed up the algebra piece at the end, or the trig piece at the end.
I don't because the teacher pulled up something that we were supposedly learned in the first year of the 2-year course. And none of us remembered. And it was literally 2-question quiz. So 50% of
was
the
one
answer
question
came from one thing, which wasn't even related to what we were doing. And the first step was using that process. I think it was like partial fraction, something or the other.
Yeah.
Which I still don't know how to do.
Calc 2 teaches that one.
Yeah. Okay.
Don't worry, so The reason that this company actually hired me to work on the next set of books is because the person that they actually had in place that's been doing all the rest of the books basically taps out of calculus because he hasn't taught or done it in so long that he just doesn't remember any of it. So it's like, it's not something, if you don't use it, you're not going to remember it, in all honesty. Especially like the harder things, like when you get into Calc 2, especially the integration rules, you got the partial fractions, which involves breaking up fractions, but it also involves systems of equations. And if you don't remember how to do systems of like 3 variables and stuff like that, it can become very complicated. So.
Yeah, it was like one of those things like, learn this now, you will be expected to know this in the future. And then you never used it for like a year and a half.
Yeah, and it's like, oh, by the way, now you need it. It's like, see, as a teacher, I would have spent, depending on how long my classes were, at least some time going over that. When I teach Calc 2, when I go to partial fractions, I actually spend time showing them how to add fractions together because most people don't remember how the common denominator works and all that other stuff. I spend time doing that because that's where I notice most of the students mess up partial fractions, and I spend time doing the system of equations because I know they're going to screw that part up. So it's like I make sure you understand the pieces before I teach you the hard stuff afterwards.
The easy stuff fades away once you've learned the like
Yeah.
fifth iteration of
Yeah,
cosine.
absolutely. And then hyperarc cosine.
Hyper cosine. Probably more.
All right.
There probably is like astrophysics or quantum physics. I don't know.
All right. Show me that cosine, the hypercosine of x plus the hypercosine or hypersine of x equals e to the x.
Okay.
Go back to the definitions. One of the very first things, the 2 things you try to write down at the very beginning slide. That's what you're going to need for this one. Just those 2 things. Namely why I told you to make sure you wrote down those 2 things. My high school kids think I just make up things randomly. It's like, do this. Why? Trust me, you're going to need it in a minute. All right, so what's hypercosine? What's hypersine? Okay. So I can put those together. All over 2. And that cancel out. So I'm left with 2e to the x over 2, which equals e to the x. That's it. All right. Yes, this is a product rule. So remember the product rule. Set up your f of x and your g of x. So what's the derivative of hypersecant of x? I'm going to have to go back because I don't remember these. I didn't write them down. All right, so the derivative of hypersecant is negative hypersecant hypertangent. And the derivative of tangent is hypersecant squared x. So now remember, it is the derivative of the first. So we've got negative secant hx tangent hx times the second plus the derivative of the second times the first. So we've got negative secant hx tangent squared x plus secant h to the third x. Yeah, start writing smaller on these. So at this point, you've done your derivative correctly, you've done your product rule correctly. But we can simplify this. All right, any questions to there? Or are we good to that one? Okay. All right, so now we can pull out a secant h of x. And we're left with negative tangent h squared plus secant squared x. So the only rule that we have is 1 minus tangent squared x equals secant that. So if I move the tangent over, I have secant squared x plus tangent squared x. Or, sorry, tangent h squared x. But that has a negative sign there. And that has the plus sign there. If I change my signs, they're all going to change. So I think that's literally as far as we can go. Or did I mess up a sign on any of them? I don't think I did. Nope, that's positive. Just want to make sure I didn't mess up my signs on any of them. That's negative. That's positive. So actually, that right there is as far as I go. That doesn't help me. And that's the thing, like sometimes why I like doing some of these problems like this is that you get into the mentality that you have to be able to simplify things and you go down that rabbit hole and it's like, okay, it's like sometimes you just can't. Like this one, it looks like it might work. That's why I did that. I'm like, okay, this looks like it might work, but it doesn't. Even if I pulled out the negative sign, I can get the tangent squared x positive, but then my secant is negative again. So well, there's always that possibility. It's like, I guess, so actually, we could do one thing. I just don't know if it's actually going to make this problem any simpler. Let's see if this actually makes the problem any simpler. So I could do this. Which then is, so I have negative tangent, or actually I have negative 2 plus 1. That doesn't really make it any simpler. Yeah, but
Oh, actually, if you multiply out the secant h, then you could like do oh.
no, that's the derivative. Yeah. And I don't even think changing them to sine and cosines are really going to help you much in this one. So it's like, again, sometimes you can, sometimes you can't. So I would say when you go through and do your test, because time is the essence when you're doing your tests. When you're trying to simplify things down, if you get to a point where it's like, okay, you think you're going down a rabbit hole, stop, go do the rest of the test, and you can always go back to it afterwards. All right, don't spend a ton of time wasting on trying to get this one problem down and then you blow the rest of the test. So I did put it in kind of an order, so it's like this is the end of the test anyway. So, but there are other trick problems even in the other sections too. So, all right. But that goes with anything. It's like if you're going down a rabbit hole, even if you're going down a rabbit hole at work, stop, put it aside for a little bit, and come back to it. And don't sit there and waste a ton of time. Although I'm totally, like, I've done that I don't know how many times. All right, last one. All right, take a minute, try this one, and then I'll go through and do it out. you will be using in this one 2 rules. You have the product rule and the chain rule. Mm-hmm.
Oh, I thought that was a strip chain rule.
Nope, there's a T in the front.
Oh. Okay.
But yeah, when you look at the answers, I'm going to post the answers for the test, the review test on my website, on the website. When you look at the answers, the one that there is that actual question that is T, I did the entire problem with X. And then I went back and I'm like, why did I typed the problem out. Why did I use T? I just realized you have to use the chain rule twice in this problem. No. Although I don't know what the answer is actually going to be in a second. So. Then we have square root of x squared plus 1 times x over. Okay. That's good.
Stage of confusing both functions and things.
Yes. All right, so we've got the derivative of fx, x is 1, or the derivative of x is 1, so that's that. The derivative of hypercotangent of the square root of x squared plus 1, we have to do a chain rule, so u is the square root of x squared plus 1, which we then have to do a chain rule on that. So we've got derivative of that is 2x over 2 square root of x squared plus 1, which is equal to that. And then we can plug that back in for g of x. So it's the derivative of cotangent, which is cosecant squared u, which is that, times the derivative of u. We can't cancel out the x squareds, the square root of x squared plus 1, because 1 is inside of the cosecant and 1 is outside of the cosecant. So, let's duplicate this. Let's do this the bottom. Now we have to do our product rule. So we've got derivative of the first, which is 1, times the second, derivative of the second, I missed the
Wait,
x.
is that negative?
Yes. So actually, let me just change that to a negative sign. Actually, no, I'm going to leave that through for a second. I forgot the x in front. Times the original one, which was just x.
X?
Yeah, there was because the x is on the top up here.
Oh, okay, that's one of the things you did. Okay.
Yeah.
So you do an X squared or something? Maybe that's right.
It was, yeah, it's going to be negative x squared. There we go. That's our final answer. I do not think we can simplify that down.
Line going back and stuff.
Yeah.
Man, right, left. If that's even possible.
Which chain rule hold did you fall down?
I think I just dropped the +1.
I think I fell down the cotangent, the hypercotangent. Get that one. That one.
The answer sheet for the test is not just, here's the answer. I did out all the problems. So you'll see step by step how I would have done the problems. Just like I'm doing on the board here.